Okay, the last thing I want to cover today is chapter 9.7, units of concentration. So when we have a solution, the concentration is actually really important, and we want to be able to talk about it quantitatively. There's a big difference between a relatively dilute concentration that is not very much solute versus a very concentrated solution with lots of solvent. Sorry, with lots of solute. So if we can talk about this quantitatively, then that gives us a powerful tool for making predictions about how they'll behave and talking about it in a quantitative way. So there are lots of different units that each have their purpose. As chemists, we'll most often use what's called molar concentration. So this is the concentration that is most relevant to a chemist. It's the concentration that will sort of determine equilibrium and things like that. So the molar concentration is defined as moles of solute over liters of solution. And I really want to emphasize that that's liters of solution, not liters of solvent. So if I want to make a solution of, say, sodium chloride, if I want to make a 2.0 molar solution of sodium chloride, that capital M means it has a molar concentration of 2.0 molar. Or in other words, 2 moles of sodium chloride for every liter of solution. So if I wanted to make that, sorry, let me get the right figures up here. Then there would be a 3-step process. First, and this is obviously not sodium chloride, they've got some sort of yellow salt, I don't know what that is. But I would weigh out, if I'm using a 100 milliliter volumetric flask, then since my volume is 1/10 of a liter, then I would want 1/10 of 2 moles. So if I'm making 100 milliliters of a 2 molar solution, I would weigh out 0.2 moles of my solute. And then I would pour that into what's called a volumetric flask. And that's the piece of glassware that they're showing here. And then I would add just enough water to dissolve that solute. And I would swirl it around until it is dissolved. And then finally I would very carefully add water now up until it reaches the mark that indicates 100 milliliters. So I'm never really directly measuring the amount of water that I add. Instead, I'm just adding however much water it takes to make 100 milliliters of solution. And because the solute particles themselves have their own volume, and the volume changes over the process of solvation, it's just not worth it to try to calculate ahead of time how much water you'll need. It's probably about 100 milliliters, but not precisely 100 milliliters. So if you want to be very precise, you'll measure out the amount of your solute, and then you'll just add water until it reaches the mark. Okay, and we're going to, next week, do a lot of problems where we deal with molar concentration in a quantitative way. And it's going to be sort of an important part of our mathematical calculations from here on. But I want to point out that just like any unit that has a ratio of 2 different quantities, it can be used as a conversion factor between those 2 quantities. So if I'm walking at 2 miles per hour, I can use that velocity to figure out how many hours it takes for me to walk a certain number of miles, or how many miles I can walk in a certain number of hours. The velocity, 2 miles per hour, can be thought of as a conversion factor between miles and hours. So molar concentration can also be thought of as a conversion factor between moles of solute and liters of solution. And we'll be using it in that way a lot from now on, but not quite today. So for today, you just want to know how to calculate the molar concentration. You figure out the number of moles of solute, and you divide by the liters of solution. Relatively straightforward. And we've got a quiz that will walk you through that. So there are a few more units of concentration that, as a chemist, you know, is a little bit less common in a chemical laboratory. But out in the industrial world, in the medical world, and you know, other places in sort of the real world, these other units of concentration are actually a lot more common. So there are different percent concentrations. And so there's three different ones we're going to look at. There's mass percent. And there's volume percent. And then there is mass volume percent. And so in mass percent, you're going to take the mass of the solute divided by the total mass times 100%. So the total mass would be the solvent plus the mass of any solutes that you may have. And if you have lots of solutes, then that might include lots of things that you have to sum up here. So mass percent is really pretty straightforward. If I take 5 grams of sodium chloride and I dissolve it in 100 grams of water, then that would be 5 divided by 105 times 100%. Let me just really quickly figure out what number that would be. Okay, sorry, 5 divided by 105 times 100. You know, that would be 4.76 mass percent. Okay, the next one is volume percent. So this is volume of solute over the total volume. Times 100%. And this is most often used when you're mixing two liquids. If I were to take ethanol and mix it in water, if I have a 50% by volume ethanol solution, then that means that I've got 50 milliliters of ethanol and 50 milliliters of water, and they mix together to make 100 milliliters of solution. So volume is most often used in liquids. And then mass over volume would be mass of solute divided by volume of solvent. And that's different than the volume of solution, like in molarity, and times 100%. So we'll see later on why this is important. The mass volume percent is most useful for when you're looking at particular properties of solutions that depend on this ratio. It seems a little bit strange right now, but it's actually really important for what we'll later call colligative properties. So these are the percent units of concentration. There are two more, sorry about that, parts per million and parts per billion. So parts per million and parts per billion are like a mass percent usually, but it's going to be, sorry, I should be clear. Parts per million and parts per billion are actually very versatile. You could use parts per million in terms of grams, so it'd be like a mass over mass percent, or you could use parts per million in terms of counting the solute particles and counting the solvent particles. And so I'm going to just use it sort of generically. This will be the number of solute over the number total. So this could be like the grams of solute over the total grams, or maybe the number of moles of solute over the total moles, or even volume, volume of solute over total volume. But the point is that we're now going to multiply this by 10 to the 6th. And so parts per million is used when we're talking about things that are in pretty low concentrations. If you're talking about like metal cations in your drinking water, hopefully you don't have a whole lot of certain types of metal cations in your drinking water, and you'll measure them in parts per million or parts per billion even, which is the solute number over the total number times 10 to the 9th. So if I have only 3 solute particles for every billion total particles, then that would be 3 over a billion times 10 to the 9th would give me 3 parts per billion. And this parts per billion then would be like if I were measuring lead in my drinking water. I really want to have as low an amount of lead ions as possible in my drinking water, so I would hope that it's measured in parts per billion. I'm not going to stress these too much. On the quiz you'll see we do a mass percent, but I really, as a chemist, am most interested in the molar concentration, and so that's what I want you to be focusing on as well.